Okay guys, hopefully this loaded okay for you and you are able to pull it up on your phone or computer so you can easily copy the notes. If you would like, you can also look at the notes in the book, but here I will be explaining them in a little bit more detail as if I would in class. Okay, so we are going to start chapter 8. This chapter is about similarity. And 8.1 is specifically covering similar polygons, okay? So our first core concept here, corresponding parts of similar polygons. It says, in the diagram below, triangle ABC is similar to triangle DEF. You can write, okay, so as I would say this, I would say triangle ABC is similar to triangle DEF. Okay, whenever I want to write that though, I write this triangle ABC. Okay, and then I make this little squiggly line, okay? Almost like the top half of a congruent sign without the equals on the bottom is similar to triangle DEF. A similarity transformation preserves angle measure. So then maybe that's important, so I should underline it, preserves angle measure. So corresponding angles are congruent. A similarity transformation also enlarges or reduces side lengths by a scale factor of k. So that should kind of sound familiar from something that we've done earlier this year if you remember doing dilations. Okay, so corresponding side lengths are proportional. So corresponding angles here, we have angle A is congruent to angle D. Angle B is congruent to angle E, and angle C is congruent to angle F. Okay, so if we're looking at our two triangles here, those are our corresponding angles. Okay, then we have ratios of corresponding side lengths. Okay, so if I'm looking at the sides that correspond to go with one another, okay, DE is my new figure, so it's going to go on top. Okay, it's a part of the new figure, I should say. So it's going on top of our fraction or in the numerator. And on the bottom, what goes with that is AB. Okay, well I can set that equal to, because that proportion is going to be equal to every other one in that triangle as well. Okay, so DE over AB is equal to EF over BC, which is equal to FD over CA, okay, and all of those together, okay, equal K, our scale factor. Okay, so if I was to simplify, or if they're divisible, go ahead and divide it out, you're gonna get the scale factor K, and that's the difference between the two. Okay, all right, so then we're gonna scoot on up here to example 1. Okay, using similarity statements. It says in the diagram, triangle RST is similar to triangle XYZ. Part A, find the scale factor from triangle RST to triangle XYZ. Okay, so I'm starting with RST, so maybe I write like this is my first triangle and then I'm going over to my second. Okay, so if I look up above, remember our second triangle always went on top. Okay, so that's important to note here. Okay, so if I put 12, okay, XY over RS, which is 20, okay, and reduce down, okay, that is equal to, both of those are divisible by 3, both are divisible by 4, which would get me 3 over 5, okay, which is equal to XY over RS. Okay, and then we can continue doing this. Okay, if I want to do YZ over ST, okay, well that is 18 over 30. Okay. I can reduce that. Both of those are divisible by 6, which would leave me with 3 over 5. Okay, looks good. Those should match. So I did it right. Okay, then ZY ZX over TR is the only one I'm missing. Okay, so that would be 15 over 25, both divisible by 5, which gives me 3 over 5 again. Okay, so this 3 over 5 is our scale factor K. All right, B, it says list all pairs of congruent angles. Okay, well, if I start with angle R is congruent to angle X. Okay, and remember, if you have a hard time identifying which ones are the same, okay, it always gives you them in the correct order. So I can go back to my similarity statement, okay, and it gives it to you in the correct order. So R comes first, X comes first. Okay. So then I have angle S is congruent to angle Y. And last one is angle T is congruent to angle Z. Okay, so that was part B. Okay, and last part is C. Write the ratios of the corresponding side lengths in a statement of proportionality. Okay, so in a statement of proportionality, basically we are just going to connect everything that we did in part A and just write it as one statement together. Okay, so I have XY over RS. Okay, that is equal to YZ over ST, which is equal to ZX over TR. Okay, and that is example 1. Okay, then it says finding corresponding lengths in similar polygons. Corresponding lengths in similar polygons. If two polygons are similar, then the ratio of any two corresponding lengths in the polygons is equal to the scale factor of the similar polygons. Okay, so go ahead and turn your notes. Okay, and we should see example 2 up here at the top. Okay, so it says in the diagram, triangle DEF is similar to triangle MNP. Find the value of X. Okay, well, first I want to find a side or sides that I know correspond to one another and I know both of their lengths. Okay, so I see that I have this MN and DE. I know both of their values. So I'm going to use that one first. Okay, so I know MN and I know DE. Okay, well, that is equal to, then I have to figure out which one I'm looking for. Okay, well, I'm looking for EF. Okay, and EF corresponds to NP in this other triangle. Okay, so then I can write NP over EF. Okay, and now just go back and fill in everything that we know. Okay, well, MN is 18, so I can write 18 over DE is 15 is equal to NP is 30 over EF is X. Okay, cross multiply and divide. Okay, you have two options here. You can do that all in one step using your calculator, or you can go ahead and do it in 2 steps. Okay, that would mean I would have 18X. So I multiplied 18 by X, then I'm going to multiply 15 by 30 to get 450. Okay, so there's your multiply part, cross multiply, and then now I'm dividing to solve for X, and I get 25. Okay, and that's example 2. Okay, so scooting on up now, we have example 3, finding corresponding lengths. It says in the diagram, triangle TPR is similar to triangle XPZ. Find the length of the altitude segment PS. Okay, so I'm looking for this value in here. We can go ahead and label that with an X. Okay. Well, I know that TR in this triangle corresponds to XZ. Okay, well, TR is split up here. Okay, if I see, so TR in all is a 6 plus 6, and XZ is 8 and 8. So 8 plus 8. So that gives me 12 over 16. Both those numbers are divisible by 4, which will give me 3 over 4. Okay, well, I know PY, okay, so I did that to find my scale factor because I don't have anything to work off of here, okay? So this scale factor, is 3 over 4. So that's going to help me find PS over PY. Okay, we know that's going to be equivalent to 3 over 4. Okay, so I don't know what PS is, so I'm going to fill in an X. PY is 20, and that's still equal to 3 over 4. So again, cross multiply and divide here. Okay, you can do it in one step, or you can do it in two. If you'd like to do it in two, it would be 4x equals 60. Divide by 4 on both sides, and you are left with x, or PS, is equal to 15. Okay. All right, that was example 3. So moving on up now. Theorem 8.1 says if two polygons are similar, then their ratio of their perimeters. Okay, think back, perimeter, it's like if I was trying to find out how much fence I needed to buy. Okay, so that's the distance around, okay, an object. So if two polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding side lengths. Okay, so to find perimeter, we're going to add up all of our sides. Okay, so I'm going to say that I'm starting with KLMN, and I'm going over to PQRS. Okay, so that PQRS needs to go on top of everything that we're doing here. Okay, so if I start here, I have PQ plus QR, that's a Q there, plus RS plus SP all over, okay? That helps me find the perimeter, okay? So really this is capital P of our PQRS. Okay, that is over, then I need to find the perimeter of my other one. Okay, so that would be KL plus LM plus MN plus NK. Okay, again, that was the perimeter of the other shape. Okay, that proportion, okay, is the same as if I split up each one of these. Okay, and we know from earlier, okay, all of those individually, okay, are the same, and they're equivalent to our scale factor, K. Okay, so in the end, basically we can say that our perimeters, okay, the ratio of our perimeters is the same as our scale factor. Okay, now looking at example 4, okay, it says a town plans to build a new swimming pool. An Olympic pool is rectangular with a length of 50 meters and a width of 25 meters. So you can see that in this picture right here. The new pool will be similar in shape to an Olympic pool, but will have a length of 40 meters. Okay, so this length of our new pool is 40 meters. Find the perimeters, of an Olympic pool and the new pool, okay? Well, I can find the perimeter of the Olympic pool now. I have enough information, okay? Well, if this side is 25, then I know that this side is also 25, and this side is 50, okay? So you can add those all up, or you can write that as 2 times 25 plus 2 times 50, which would give us 150 meters. Okay. Now looking at our Olympic pool, the length of the Olympic pool is 50 meters and the width was 25. Okay. And I know my new pool that I'm building, okay, the length is 40. Okay, so the ratio of the lengths is given to us. Okay, so that would be 40 over 50, okay, which we know is the same as 4 over 5. Okay, so think of this as our scale factor here. Okay, so you could do this and you have two options here. First, you could solve for the width. Okay, so I know the lengths are 4 over 5. Okay, the width of the Olympic pool is 25. Okay, and I know that goes with 50, so that needs to go on the bottom. And then I don't know what the width is of our new pool. Okay, so that would get you what? 5x equals 100. 100 divided by 5 would be 20. Okay, so then I can find the perimeter. Okay, so it'd be 2 times 40 plus 2 times 20. Okay, which would give us 80 plus 40, which would be 120 meters. Okay, so that kind of took us 2 steps really to solve there. Okay, or we know by this theorem that we just said that the perimeters themselves have the same scale factor, K. Okay, so instead of solving for the width, which really that's not what they're looking for, okay, it did help us find what they're looking for, but instead we could immediately jump to 4 over 5 equals x over 150, okay, this perimeter. Okay, cross multiply and divide, and again, you're gonna find that x is equal to 120 meters. Okay, and that is the perimeter of the new pool. Oops. Okay, and that is the answer that they were looking for. Okay, so you have 2 options there of how you wanna solve that problem. Either one will work. Okay, and that was example 4, so whenever you get done there, if you need to pause it here, you can. Go back and watch it again, whatever you need to do, but then turn the page when you get done there. Okay, last page of notes here for 8.1. Okay, we have another theorem. Okay, it says theorem 8.2, areas of similar polygons. Okay, if 2 polygons are similar, then the ratios of their areas is equal to the squares of the ratios of their corresponding side lengths, which again we know is the same as that scale factor. Okay. Okay, one thing I want to point out here is this analyzing relationships. It says when 2 similar polygons have a scale factor of k, the ratio of their areas is equal to k squared. Okay, remember area is always measured in whatever unit we're measuring in, squared. Okay, so like feet squared, meters squared. So our scale factor is going to be squared as well. Okay, so looking here, I have the area. Again, we're gonna work from left to right. So this is my first polygon. This is my second. Okay, so the area of PQRS goes on top over the area of KLMN. Okay, those are equivalent, okay, to the squares of the ratios of their corresponding side lengths. Okay, so their corresponding side lengths, PQ over KL, but then I need to square that for it to be equivalent to the area. Okay, so QR over LM, all squared. RS over MN, all squared. I'm gonna run out of room here. SP over NK all squared, and all of that, okay, itself is equal to their scale factor squared. So K squared. Okay, moving on to example 5. In the diagram, triangle ABC is similar to triangle DEF. Find the area of triangle DEF. Okay, well, I know that the area of triangle ABC is over the area of triangle DEF. Okay, and I know that that is the same thing, okay, as these two sides that I can see that I know both are lengths. So AB over DE all squared. Okay, well, I know the area of triangle ABC, so I can fill that in. Okay, let's go underneath here. So we have 36 over, I'm looking for the area, so I'm going to call it capital A, is equal to, okay, ABC goes with AB, so that is 10 over 5 squared. Okay, if you remember back to our exponential rules or exponent rules, okay, if I give this square to the top, I also have to give it to the bottom. Okay, so in order to keep this equivalent, I get 10 squared, which is 100, over 5 squared, which is 25. Okay, cross, multiply, and divide. Again, you can do this in your calculator in one step if you'd like, or you can write it out. If you'd like to write it out, that would be 100A is equal to 25 times 36, which is 900. Okay, divide by 100. Okay, think of these zeros as canceling each other out, which is the same as 9 divided by 1. So A is equal to 9. Okay, which means that the area of triangle DEF, so I'll put A, triangle DEF, is equal to 9, measuring in centimeters here, so it would be centimeters squared as our final answer. Okay, last example, example 6. Okay, decide whether ABCDE and KLQRP are similar and explain your reasoning. Okay, so the first thing that I notice here, so let's see here, for example, 9 over 6. Okay, is that really equal to 6 over 4? Okay, if I reduce these are both divisible by 3. Okay, so that would give me 3 over 2. These are both divisible by 2, which would again give me 3 over 2. Okay, so they are the same. Okay, and if you kept going around and checked each one, you would see that they are equivalent. Okay, so I can say then that the corresponding sides are proportional with a scale factor of 2/3. Okay, but then the other thing that we need to look at, okay, if we think back to our very initial core concept here, okay, of our similar figures, okay, we also need all of our corresponding angles to be the same. Okay, that's the other big part of corresponding polygons, okay? So looking here, the only angles that I see are congruent are angle A and angle K. I know nothing else about any of my other angles, okay? And again, if it's not marked, we can't assume it to be true. Okay, so but corresponding angles are not all congruent. Therefore, these figures are not similar. Okay? So now that we are done, okay, that was example 6, so that was the last example. If you flip the page, you should see 8.2 at the top, so we're gonna stop there, okay? So now that we are done taking notes, okay, I want you to look back through the theorems and the examples we've done, and I want you to prepare any questions that you may have for me tomorrow before we start working on an in-class activity and a homework assignment that you will do in class with me. Okay, so I hope you liked this. We got a few more to go.